The ground underneath one of the most watched volcanoes on Earth moved last week in a way it has never moved before, and the scientists who have been monitoring it for decades are not using the word reassuring. It started with a number, not a dramatic number, not the kind of number that appears in disaster films or emergency broadcasts. A quiet number, logged automatically by a seismic sensor buried in the flank of the mountain, transmitted to a monitoring centre and added to a database that has been accumulating measurements for the better part of 40 years. The number described a tremor, a low-frequency tremor originating from a depth that the monitoring team had not previously associated with this particular kind of signal at this particular volcano. They noted it, they flagged it, they waited for the next reading. The next reading was larger, the one after that was larger still. By the time the fourth reading came in, the lead volcanologist on duty had already placed 2 calls. One to the agency director, one to a colleague at a university 3 countries away who had spent the previous decade studying exactly this type of seismic signature at exactly this type of volcanic system. The colleague picked up on the second ring. The conversation lasted 40 minutes. Neither of them slept that night. What they were looking at is not a simple thing to explain, which is part of why the public communication around it has been careful to the point of opacity. Official statements have described the activity as elevated and worthy of continued monitoring. Those words are technically accurate. They are also, in the specific context of what the instruments are showing, a significant understatement of why the people reading those instruments are worried. To understand the gap between what the official language says and what the scientific data suggests, you have to understand what this volcano is, what it has done before, and why a tremor at an unusual depth from an unusual source means something different here than it would mean almost anywhere else on the planet. The volcano sits above a subduction zone. That single geological fact contains within it an entire chain of consequences that distinguishes it from the volcanoes most people picture when they hear the word. A subduction zone is a place where one tectonic plate slides beneath another, descending into the mantle at an angle that carries cold, wet oceanic crust down into rock hot enough to partially melt it. The water released from that descending plate lowers the melting point of the surrounding mantle rock, producing magma that rises through the overlying crust and eventually erupts at the surface. This is the mechanism behind the volcanoes of the Pacific Ring of Fire, the chain of volcanic systems ringing the Pacific Basin that includes some of the most historically destructive eruptions in human memory. It is also the mechanism behind this specific volcano, which sits above one of the most geometrically complex subduction configurations on the planet, where the descending slab has been imaged by seismic tomography as a fractured, irregular surface rather than the smooth, continuous sheet that simplified diagrams of subduction zones depict. That fractured geometry matters. It matters because it creates pathways. Pathways for fluids, for volatiles, for the water and carbon dioxide and sulfur compounds that are released as the subducting plate heats up and transforms. Those fluids travel upward through the fracture network in the overlying crust, and when they encounter a body of partially molten rock, they change its behaviour. They lower its viscosity. They increase the gas content dissolved within it. They alter the pressure balance in ways that can, under certain conditions, push a magmatic system from passive degassing towards something more energetic. The low-frequency tremors the monitoring team recorded last week are consistent with fluid movement through fractures at depth, not surface water, not rainwater infiltrating the volcanic edifice, fluids from depth, from the zone where the subducting slab is releasing its stored volatiles into the system above it. That is the detail that made the colleague 3 countries away pick up on the second ring. The volcano's recorded history spans approximately 400 years of documented observation, supplemented by geological mapping of deposits that extend the record back several thousand years. Within that combined record, there have been 3 major eruptive episodes of sufficient magnitude to alter the regional landscape. The most recent of those episodes occurred in a decade within living memory of some of the older researchers now monitoring the system. The deposits it left behind, the thick layers of pyroclastic material, the lava flows whose margins are still visible in the topography, and the lahar channels carved by volcanic mudflows that followed the eruption for years afterward tell a story of a system capable of producing events at the upper end of the volcanic explosivity scale. Not the absolute maximum, not the caldera forming super eruptions that reshape continents and alter global climate for years, but well above the category of nuisance eruption, well above the category of manageable hazard, and into the category where the question is not whether people will be affected, but how many and over what geographic area. The Volcanic Explosivity Index, the scale researchers use to compare eruption magnitudes, runs from 0 to 8. A value of 0 describes a gentle, effusive eruption producing lava flows that move slowly enough for people to walk away from them. A value of 8 describes an event producing more than 1,000 cubic kilometers of material, an eruption of a scale that has not occurred in recorded human history, and that the geological record shows happening roughly once per 100,000 years on average. The most recent major eruption at this volcano has been assigned a value of 5 by the researchers who mapped its deposit volumes and estimated its column height. A 5 on that scale is a major eruption by any measure used outside academic volcanology. It is the category that includes the 1883 eruption of Krakatau, which killed more than 36,000 people, primarily through the tsunamis generated by its collapse, and the 1981 eruption of Mount St. Helens, which removed the northern flank of the mountain in a lateral blast and deposited ash across 11 states. A 5 is not a reassuring category for a volcano showing new activity patterns that its monitoring network has never previously recorded. The monitoring network itself deserves attention because it is one of the more sophisticated volcano observation systems currently operating anywhere in the world, and the fact that it is producing data the scientists find alarming is not an artifact of inadequate instrumentation. The network includes broadband seismometers capable of detecting ground motion at frequencies ranging from the microseismic to the infrasonic, installed at multiple depths in boreholes drilled into the volcano's flanks to reduce the noise contamination that surface instruments experience. It includes continuous GPS receivers measuring ground deformation at millimeter precision, capable of detecting the inflation or deflation of the volcanic edifice that accompanies movement of magma at depth. It includes gas monitoring stations measuring the flux of sulfur dioxide, carbon dioxide, and hydrogen sulfide from fumarolic vents on the summit and upper flanks, because the ratio and absolute flux of those gases carries information about the depth and temperature of the magmatic system releasing them. It includes a gravimeter network measuring subtle changes in the local gravitational field that can indicate mass redistribution within the volcanic edifice. And it includes a tiltmeter array, measuring the slight tilting of the ground surface that accompanies pressurization or depressurization of the shallow magmatic system beneath the summit. All of those instruments are producing data simultaneously. All of that data feeds into a real-time monitoring system that generates automated alerts when predefined thresholds are exceeded. Several of those thresholds have been exceeded in the past week. Not all of them. Not the ones associated with the most immediate pre-eruptive signals, but enough of them in a pattern that the senior volcanologists on the monitoring team describe privately as coherent, that the discussion at the monitoring centre has shifted from routine surveillance to active hazard assessment. The distinction between those two operational modes is not just procedural. It reflects a judgment about whether the system is behaving within its established baseline of activity, or whether it has entered a new behavioural regime whose trajectory is not yet determined. That judgment is the hardest one in operational volcanology, because it has to be made with incomplete information about a process occurring kilometres below the surface in rock that cannot be directly observed, using proxy measurements whose interpretation requires assumptions that experienced scientists sometimes disagree about. The disagreement among scientists about how to interpret the current data is itself a data point, not a reassuring one. When the monitoring team is unanimous that the signals are within normal background variation, the discussion is short and the operational posture does not change. When experienced volcanologists who have spent careers studying this specific system are discussing the same data set and reaching different conclusions about its significance, the range of interpretations itself tells you something about where the system sits in its behavioural space. It sits in a place where the data is ambiguous enough to support more than one interpretation, which means it sits in a place where certainty is not available, and where decisions about hazard communication and preparedness have to be made under genuine scientific uncertainty. That is the uncomfortable operational reality of volcano monitoring at a system that has not erupted in decades and whose current activity falls outside the patterns established during the most recent eruptive cycle. The most recent eruptive cycle is important context because it established the observational baseline against which current data is compared. During the period leading up to the last major eruption, the monitoring network logged a specific sequence of precursory signals that have since become the reference pattern for pre-eruptive activity at this volcano. That sequence included elevated seismicity at shallow crustal depths, followed by measurable ground inflation detected by the GPS network, followed by a step change in sulfur dioxide flux from the summit fumaroles, followed by the emergence of shallow hybrid earthquakes, whose waveform characteristics indicated fracturing of brittle rock immediately above the magma reservoir. That sequence, in that order, over a period of weeks to months, was the observable signature of the last eruption's preparation. Emergency managers and volcano monitoring agencies in the region have contingency plans built around the recurrence of that specific sequence. The current activity does not match that sequence. It does not begin with elevated shallow seismicity. It begins with low-frequency tremors at unusual depth. That distinction is the crux of the scientific disagreement, because low-frequency tremors at depth can mean several things, and the interpretive frameworks for distinguishing between them are not universally agreed upon. One interpretation is that the tremors reflect movement of magmatic fluids through the lower crust as a new batch of magma ascends from the mantle source region toward the shallower storage zone that fed the last eruption. Under this interpretation, the current signals represent an early-stage precursor to a new eruptive cycle, earlier in the process than anything the monitoring network captured before the last eruption, because the network was less sensitive in its earlier configuration. The tremors are, in this reading, the sound of something new arriving from below, something that has not yet reached the storage zone where it would begin producing the familiar shallow seismicity and ground inflation of the established precursor sequence, something that is still on its way. A second interpretation holds that the tremors reflect a different kind of fluid movement entirely, specifically the migration of hydrothermal fluids through a fracture system that has been reactivated by stress changes in the lower crust, unrelated to a new magmatic intrusion. Volcanoes are not only magmatic systems, they are also hydrothermal systems, circulating heated groundwater through their interiors and creating a complex plumbing network that responds to changes in the stress field of the surrounding crust. Tectonic earthquakes in the region, a sequence of which occurred approximately 6 weeks before the onset of the anomalous tremors, could have altered the permeability of the lower crustal fracture network sufficiently to produce the observed signal without any involvement of ascending magma. Under this interpretation, the current activity is a hydrothermal response to a tectonic perturbation, transient in nature and likely to subside without progressing toward eruptive behavior. The third interpretation, the one that the most cautious voices on the monitoring team are advancing, is that both processes are occurring simultaneously and that their interaction is what makes the current situation genuinely uncertain. A hydrothermal system perturbed by tectonic stress changes becomes more permeable. A more permeable pathway facilitates the ascent of magmatic fluids from the deep source region. The ascending fluids encounter the hydrothermal system and alter its chemistry and pressure distribution. The altered hydrothermal system produces gas emissions that mask or amplify the magmatic signal in the surface measurements. The result is a monitoring dataset that contains contributions from multiple, overlapping processes operating at different depths and on different timescales, and that cannot be cleanly decomposed into its component parts with the data resolution currently available. That interpretive complexity is not a failure of the monitoring system. It is the honest scientific description of what volcano monitoring at depth-limited resolution looks like when the system is doing something new. The depth of the initial tremor source is the specific detail that has most engaged the international volcanological community in the days since the monitoring team's first public communication. The tremors are originating from approximately 35 kilometers below the surface. 35 kilometers is below the base of the crust in this tectonic setting. It is in the upper mantle. A seismic signal originating from the upper mantle beneath a subduction zone volcano does not appear in most volcano monitoring textbooks as a standard precursory signal, because most volcano monitoring programs do not operate instrumentation sensitive enough to reliably locate sources at that depth. The fact that this network can locate sources at 35 kilometers is a consequence of the borehole seismometer array, whose depth-installed sensors provide the three-dimensional source location resolution that surface networks cannot achieve for deep signals. The fact that those sources are producing low-frequency tremors at 35 kilometers depth means that something is moving or fracturing or releasing fluids in the uppermost mantle beneath this volcano. That something is not the hydrothermal system. The hydrothermal system does not extend to the upper mantle. Whatever is producing those signals is deeper than the hydrothermal circulation and shallower than the subducting slab. It is in the zone where mantle rock, partially hydrated by fluids released from the subducting plate below, can begin to partially melt under the right pressure and temperature conditions. The right pressure and temperature conditions for partial melting in the mantle wedge above a subducting slab are not exotic. They are the standard conditions that generate magma at every subduction zone volcano on the planet. What is specific to the current situation is the timing and the rate. The rate at which the tremor source is apparently migrating upward through the lower crust, estimated from the progressive shallowing of the tremor focal depths over the past 8 days, is faster than what has been observed in published case studies of magmatic intrusion sequences at comparable subduction zone volcanoes. Faster upward migration of a deep seismic source does not definitively mean a faster moving magmatic intrusion. Source migration rates estimated from tremor locations carry significant uncertainty that the monitoring team has been careful to quantify and communicate in its technical advisories. But the central estimate of that migration rate, combined with the depth of the initial source and the apparent trajectory of the trend, places the putative intrusion front at a depth that is approaching the base of the established magma storage zone within a time window that is measured in weeks rather than months. Weeks rather than months is a different kind of uncertainty than months rather than years. Volcano monitoring programs are accustomed to managing preparedness communication across timescales of months to years, during which there is ample opportunity for the observational picture to clarify, for the scientific community to develop consensus interpretations, and for emergency management agencies to execute graduated response protocols that match the evolving hazard assessment. A timescale of weeks compresses that process. It removes some of the iterative cycles of observation, interpretation, communication, and response adjustment that the standard model of volcanic crisis management depends on. It places the monitoring team in the position of communicating significant uncertainty about a potentially rapidly evolving situation to emergency management agencies and ultimately to the public in a form that is honest about what is not known, without either triggering premature response actions that would be costly if the hazard does not materialize, or delaying necessary preparedness actions until the situation has advanced beyond the point where they can be executed effectively. That communication challenge is not hypothetical. It is the active operational challenge facing the monitoring team right now. The agency director who received the first call a week ago has since been in daily contact with the National Civil Protection Authority, with the regional governors whose jurisdictions include communities in the potential impact zone, and with international counterparts through the World Organization of Volcano Observatories network. Those conversations have been about exactly this tension, about how to frame scientific uncertainty in a way that supports appropriate preparedness action without producing either complacency or panic in the populations that would need to act if the hazard assessment escalates. The Civil Protection Authority has experience with this tension from previous volcanic crises in the region. That experience does not make the tension comfortable. It makes it navigable, which is the most that can be said for a situation where the science is genuinely uncertain and the potential consequences of being wrong in either direction are severe. Being wrong toward underestimation at this volcano means failing to prepare populations in the hazard zones for an eruption that the monitoring signals were, in retrospect, clearly heralding. It means evacuation orders issued too late, emergency resources staged too far from where they are needed, communities lacking the information and preparation to respond effectively when the eruption begins. The historical record of volcanic disasters, attributed partly to inadequate precursory warning or inadequate response to available warning, is long and includes events within the past 30 years at volcanoes whose monitoring networks had more limited capabilities than this one. The institutional memory of those events shapes the risk tolerance of the current monitoring team in the direction of caution. Every volcanologist who has studied the Nevado del Ruiz disaster of 1985, in which a relatively modest eruption melted glacial ice and generated lahars that killed approximately 23,000 people in the town of Armero, despite warning signs that were known and documented in advance, carries that event as a professional reference point for what the cost of undercommunication looks like. 23,000 people. In a town that had been assessed as being in a lahar hazard zone, in a country with a functioning government and a monitoring agency that had documented the hazard. The failure was not primarily scientific. The failure was in the translation of scientific assessment into action by institutions and individuals with the authority and responsibility to act. Being wrong toward overestimation means issuing warnings that mobilize costly and disruptive preparedness responses, potentially including evacuation of communities near the volcano in response to signals that ultimately reflect non-eruptive subsurface processes. It means the economic disruption of communities that depend on agriculture, tourism, or other activities that cease during volcanic alerts. It means the erosion of public trust in the warning system that makes future warnings less effective. And it means the specific political and institutional costs that fall on the officials who authorize the precautionary measures when those measures turn out not to have been necessary. Those costs are real, and they shape behavior in ways that the formal structure of hazard communication does not fully account for. Officials who have authorized costly evacuations that turned out to be unnecessary face political pressure that officials who authorized insufficient response do not face until after the fact, when the damage is done and the accounting begins. That asymmetry in the timing of consequences creates an institutional bias toward waiting for more definitive evidence before escalating response, which is exactly the wrong direction for a volcanic system that may be building toward an eruption on a timescale of weeks. The communities in the potential impact zone of this volcano are not abstract populations in a hazard assessment document. They are people living in towns and villages that have grown up around the volcano over generations, whose economies and livelihoods are connected to the land in its shadow, and whose relationship to the hazard it represents varies enormously depending on age, experience, economic circumstances, and the degree to which they have engaged with the official hazard communication the monitoring agency has produced over the years. Some of those communities have members who were present during the most recent major eruption. For them, the hazard is not theoretical. It is a lived experience that informs their response to current warnings in ways that no communication campaign can replicate. For younger residents who grew up in the shadow of a dormant volcano that has been producing nothing more dramatic than steam and the occasional minor tremor for their entire lives, the hazard has a different psychological reality. One shaped more by familiarity and the absence of experienced consequence than by informed risk assessment. That generational gradient in risk perception is a consistent feature of volcanic hazard zones globally and has been documented in communities near volcanoes from Mount Etna in Sicily to Merapi in Java to the flanks of the volcanoes in the Pacific Northwest. Familiarity produces a specific kind of cognitive adaptation that researchers studying natural hazard risk perception have described as the normalization of extraordinary risk. People who live next to a volcano that they have watched throughout their lives become accustomed to its presence. Its existence in their landscape becomes part of the background, like a mountain or a river, something whose presence is noted, but whose hazard is not actively maintained in conscious awareness during the long periods of quiescence between eruptive episodes. When scientists begin communicating concern about new activity, the normalized perception creates resistance to updating the risk assessment. The volcano has always been there. It has always produced some activity. It has not erupted in a long time. These are the cognitive frames that absorb and soften warning messages in ways that the people delivering those messages find consistently frustrating. and that the people receiving them find entirely rational given their lived experience. The monitoring agency's public communication strategy for this escalating situation has been developed with those cognitive frames in mind, at least in principle. The agency has invested in community liaison programs over the past decade that involve local officials, schools, and community organizations in regular hazard education activities designed to maintain awareness of the volcanic risk during non-crisis periods. Those programs have produced measurable improvements in community knowledge of the hazard zones, evacuation routes, and appropriate response behaviours according to post-program surveys. Whether that improved knowledge translates into improved behavioural response during an actual escalating crisis is a question that has not yet been answered for this specific community, because the crisis being answered is the most significant one this monitoring system has faced in its current configuration. The programs have prepared people. Whether they have prepared them enough, and whether the preparation translates into the specific actions the next few weeks may require, will be determined by events that have not yet occurred. The hazard zones defined in the current volcanic risk assessment cover an area extending approximately 30 kilometers from the summit in directions determined by the topography of the volcano's flanks and the geometry of the valleys that would channel pyroclastic flows and lahars in the event of a major eruption. Those zones were drawn using numerical models calibrated against the deposit distribution of previous eruptions and against the physical parameters, slope angle, valley geometry, drainage network of the current landscape. The zones are not uniform circles around the summit. They follow the terrain in ways that reflect the specific flow pathways carved by previous eruptive products and the drainage networks that lahars would likely follow in the event of significant pyroclastic material being deposited on the upper flanks. Within those zones, the total population exposed to moderate or greater hazard has been estimated at approximately 240,000 people. 240,000 is not the population of a small rural area. It is the population of a mid-sized city, distributed across a landscape of farms, villages, and small towns, whose evacuation would require mobilization of transport, reception center capacity, and logistical coordination well beyond what a routine emergency response can provide without significant pre-positioning. The pre-positioning question is where the monitoring team's current assessment intersects most directly with emergency management decision-making. Pre-positioning evacuation assets, confirming shelter capacity, notifying transport operators, and beginning the communication cascade that prepares communities to move on short notice. All of those actions can be taken without declaring a formal volcanic alert or ordering evacuation. They are precautionary measures that improve the speed and effectiveness of response if the situation escalates, at a cost in resources and potential community disruption that is manageable if the measures remain invisible to the public, and if the situation resolves without requiring their full activation. The Civil Protection Authority has authorised a subset of those precautionary measures in the past 48 hours. The subset authorised reflects a judgment about where the current monitoring data sits on the continuum between background activity and definitive pre-eruptive signals, a judgment that balances the cost of preparation against the cost of false alarm, with the weight given to each side of that balance reflecting the authority's assessment of the current scientific picture and its own institutional risk tolerance. The scientific picture is not static. It is being updated every 6 hours as the monitoring network produces new data and as the team analysing that data refines its interpretations. The most recent seismic data, processed and reviewed in the past 12 hours, shows a continuation of the tremor pattern at depth, with no significant change in rate or spectral character. The GPS network has not yet recorded a deformation signal above the noise threshold. The gas monitoring stations are showing a modest but statistically significant increase in carbon dioxide flux from one of the summit fumarole fields, an increase that has been present for the past 4 days and that is within the range of variation documented during previous periods of elevated background activity at this volcano. None of those individual signals, in isolation, would be sufficient to elevate the operational alert level. Together, in the context of the anomalous deep tremors that initiated the current assessment, they form a pattern that is coherent with the deep fluid migration hypothesis and inconsistent with a scenario in which the deep signals are entirely unrelated to shallower parts of the volcanic system. Coherent with the hypothesis is the careful language of scientists who are not yet willing to say confirmed, because confirmed requires evidence that the current dataset does not provide. The evidence required to confirm that a new batch of magma is ascending toward the shallow storage zone would include a clear inflation signal on the GPS network indicating pressurization of the magma reservoir, an increase in shallow seismicity reflecting the fracturing of rock above the reservoir as the magma rises into it, and a step change in sulfur dioxide flux, indicating that magmatic gases from a fresh, high-temperature magma body are reaching the surface degassing system. None of those signals have appeared. Their absence is consistent with the intrusion being still at depth, below the zone where its presence would be detectable by the shallow monitoring components. Their absence is also consistent with the absence of any intrusion at all, and with the alternative hydrothermal interpretation of the deep tremors. Distinguishing between those two interpretations requires either additional time for the process to evolve in ways that discriminate between them, or additional observational data from measurement types that are not currently part of the permanent monitoring network. The additional observational data being mobilized in response to the current situation includes a campaign of magnetotelluric measurements designed to image the electrical resistivity structure of the lower crust beneath the volcano. Magnetotellurics is a geophysical technique that measures naturally occurring electromagnetic fields at the ground surface to infer the electrical properties of the rock below. Partial melt, hot fluids, and graphite-bearing metamorphic rocks all produce characteristic low-resistivity anomalies that can be distinguished from the high-resistivity signature of cool, dry, intact rock. A magnetotelluric survey across the flanks of the volcano would provide a snapshot of the current electrical resistivity structure of the crust that, compared against a baseline survey conducted approximately 8 years ago, might reveal changes in the fluid content or temperature structure of the lower crust consistent with a new magmatic intrusion. The comparison against the historical baseline is the key. A single snapshot without a baseline for comparison is almost impossible to interpret. The existence of the 8-year-old baseline survey, which was conducted as part of a research program studying the magmatic plumbing system of the volcano during a period of quiescence, is an unusual piece of good fortune that transforms the planned campaign from a qualitative characterization exercise into a quantitative change detection measurement. The team conducting the magnetotelluric survey arrived at the volcano 3 days ago. They have been deploying their instrument array across the northern and eastern flanks, where the modelling of the seismic source locations suggests the ascending fluids, if present, would be most likely to have altered the crustal electrical structure. The survey will require approximately 10 days to complete and process. 10 days is a long time in the context of a potentially evolving volcanic system. The results will not be available before the situation has either evolved further or stabilised. They will not determine the emergency management decisions being made in the coming week. What they will provide is a retrospective constraint on whatever happened during that week, a data set that will either confirm or contradict the interpretations being advanced in the absence of direct evidence, and that will improve the interpretive framework available for the next time a similar signal appears at this or another comparable volcanic system. That contribution to future preparedness is not trivial. The science of volcano monitoring advances through exactly this kind of opportunistic data collection during periods of elevated activity at well-monitored systems. Each crisis, however it resolves, leaves behind a richer dataset than existed before it began. The instruments deployed, the measurements taken, the interpretive frameworks tested and refined against the evolving ground truth, all of that becomes part of the scientific infrastructure available for the next event. The tragedy of volcanic disasters is not only the immediate human cost, it is also the opportunity cost of the scientific learning that could have happened if the system had been more thoroughly monitored before, during, and after the event. Every volcano that erupts with inadequate scientific coverage leaves a gap in the knowledge base that makes the next comparable event harder to understand and harder to forecast. Every well-monitored system that produces an anomalous signal, even one that ultimately does not lead to an eruption, advances the science in ways that improve the forecast capability for future events at that and comparable systems. The international scientific community's engagement with the current situation reflects the priority that volcanologists place on learning from anomalous activity at monitored systems. Researchers from volcanic monitoring programs in Japan, the United States, Italy, New Zealand, and several other countries with significant volcanic monitoring expertise have been in contact with the local monitoring team, offering analysis, sharing relevant case studies from comparable systems, and, in some cases, making arrangements to deploy additional instrumentation or provide remote analysis support. That international network, operating through the informal professional relationships that characterize the global volcanological community, functions as a distributed expertise system that supplements the local monitoring capacity in ways that no single national program can replicate through its own resources alone. Its activation in response to the current situation is itself a signal that the community takes the anomalous signals seriously, not in the sense of certainty about an impending eruption, but in the sense of professional recognition that the data merits the attention of multiple experienced eyes. The attention of multiple experienced eyes is not the same as agreement among those eyes. The scientific correspondence being shared within the informal network reflects the same range of interpretations that characterizes the internal discussion at the monitoring center. Some researchers find the deep tremor signal compelling evidence for mantle-derived fluid migration consistent with a new magmatic episode. Others are more conservative, noting that deep, low-frequency tremors at subduction zone volcanoes have been documented in multiple cases that did not progress to eruptive activity, and arguing that the current signals fall within the range of non-eruptive deep crustal processes. A third group, perhaps the most relevant for operational purposes, is not committing to either interpretation, but is emphasizing the importance of the next few weeks of monitoring data in discriminating between scenarios and urging preparedness actions calibrated to the genuine uncertainty, rather than to either the optimistic or the pessimistic reading of the current data. Preparedness calibrated to genuine uncertainty is easier to describe than to implement. The operational manifestation of genuine uncertainty in volcanic crisis management is a preparedness posture that maintains elevated readiness without triggering the full mobilization of evacuation resources, that communicates enhanced hazard potential without producing either complacency or panic, and that positions decision-makers to escalate response rapidly if the monitoring signals evolve in a direction that reduces uncertainty toward the concerning end of the interpretive range. That posture requires institutional agility, clear trigger criteria for escalation, pre-established communication protocols, and the kind of trusted relationship between the monitoring agency and civil protection authorities that allows rapid decision-making without the friction of real-time negotiation about institutional roles and responsibilities. Those institutional foundations have been built at this volcano over decades of joint exercises, collaborative hazard planning, and the shared experience of managing previous periods of elevated activity. They are being tested now in a situation whose specific character is different from anything the joint planning process was explicitly designed for. The specific character of the current situation, a deep, anomalous signal with no shallow confirmation, a scientific community divided between interpretations, a potential escalation timeline measured in weeks rather than months, and a population of 240,000 people in the hazard zone whose behavioral response to warning will ultimately determine the human outcome of whatever happens underground, is not a scenario that any single institution or planning document anticipated exactly. It is the kind of scenario that volcanic crisis management always produces in some form, because volcanoes do not follow scripts, and the situations they generate always contain elements that were not specifically planned for. The quality of the response is determined not by how well it matches a pre-existing plan, but by how well the institutions and individuals involved can adapt their capabilities, their communication, and their decision-making to the specific character of what they actually face. What they actually face, as of the latest data review completed 4 hours ago, is a system that has been producing anomalous deep signals for 10 days, that has shown no resolution of those signals in either direction, that is being monitored at a level of intensity that the network has not previously sustained for an extended period, and that is sitting in a geological and atmospheric environment where the consequences of a major eruptive episode would extend far beyond the immediate volcanic hazard. The far beyond dimension is the part of the hazard picture that most public communication about volcanic risk fails to adequately convey, because it involves processes that operate on timescales and geographic scales that are harder to communicate than the immediate dramatic hazard of pyroclastic flows and lava. The far beyond hazard at this volcano is primarily expressed through lahars. Lahars are volcanic mudflows, mixtures of water and volcanic debris that can travel down river valleys at speeds exceeding 60 kilometers per hour, with the consistency of wet concrete and the carrying capacity to transport boulders the size of automobiles tens of kilometers from their origin. They are generated when volcanic material, either freshly erupted pyroclastic deposits or older unconsolidated volcanic debris already present on the flanks, is mobilized by water. That water can come from several sources. It can come from heavy rainfall on the flanks, which is a persistent source of lahar generation at many tropical volcanoes, where eruptions have deposited loose material that remains mobile for years after the eruption ends. It can come from the melting of a summit ice cap or glacier, if present, by volcanic heat during or immediately after an eruption. And it can come from crater lakes, which are bodies of water that accumulate in the summit crater of some volcanoes between eruptive episodes and that can be violently expelled during an eruption, mixing with pyroclastic material and generating lahars of extraordinary volume and temperature. This volcano has a crater lake. It has maintained a crater lake with varying volume and chemistry throughout the monitoring period. The current state of that lake, based on the most recent field measurements and remote sensing analysis, shows a water volume and pH that are within the historical range for this phase of the volcanic cycle. The lake's temperature has shown a modest increase over the past 3 weeks that may or may not be related to the deep anomalous signals being recorded by the seismic network. Temperature increases in crater lakes can reflect enhanced heat flux from the magmatic system below, or they can reflect seasonal and meteorological influences on the surface energy balance of the lake, and distinguishing between those contributions requires continuous monitoring data of a quality and temporal resolution that the current lake monitoring program just barely provides. The lake temperature trend is being watched. It is not yet at a level that has been added to the list of elevated indicators in the monitoring team's internal status report. It is on the list of parameters receiving enhanced scrutiny. That is a different category, but it is not the same as reassurance. A crater lake in the context of a potentially escalating volcanic system represents a specific kind of compounded hazard that volcanologists describe as a phreatomagmatic eruption risk. Phreatomagmatic eruptions occur when rising magma contacts a body of water, producing violent, steam-driven explosions whose energy budget vastly exceeds what the magma's own volatile content would generate in a purely magmatic eruption. The interaction of magma and water is explosive in a literal physical sense because the thermal energy released when magma vaporizes water produces a pressure pulse that fractures both the surrounding rock and the magma itself into very fine particles. Those fine particles are carried high into the eruption column. They travel further from the source. They cool more slowly and pose inhalation hazards at distances from the vent where coarser pyroclastic material would have already settled. And the initial explosive energy of a phreatomagmatic eruption can be sufficient to trigger slope failures on the volcanic edifice that generate additional hazards well beyond the eruptive column itself. The combination of a crater lake, a potentially ascending magmatic intrusion, and a history that includes at least one major eruptive episode with significant phreatomagmatic components is the specific combination that places this volcano in a category of particular scientific concern. It is not the only volcano on Earth with that combination of characteristics. Several of the most closely watched volcanic systems in the world share it. What makes the current situation specific to this volcano is the deep origin of the anomalous signals, which suggests a process originating well below the level at which the monitoring network's pre-existing interpretive frameworks were calibrated, and the timescale of the apparent upward migration, which provides less runway for the standard graduated response model than most volcanic crisis management protocols assume. The standard graduated response model for volcanic crises operates through a series of alert levels, each associated with a specific monitoring threshold and a specific set of recommended protective actions. The transition between levels is designed to provide progressive escalation that matches the observable evolution of the hazard and provides the public with a graduated preparation experience rather than a sudden jump from routine to emergency. That graduated experience is designed to support the cognitive and behavioural adaptation that effective response requires, giving communities time to accept the elevated risk, make preparations, and develop the situational awareness that informs good decision-making during an active crisis. The model works well when the pre-eruptive signal sequence follows a pattern that the alert level criteria were calibrated against, which, for most volcanoes, means the shallow signal sequence associated with magma ascending into the upper crust and pressurizing the shallow reservoir. When the pre-eruptive sequence does not follow that pattern, when it begins with anomalies at depths below what the shallow monitoring components can detect, the graduated alert model faces a calibration problem. The early stages of the process may be occurring without triggering the criteria for alert level escalation, producing a situation in which the underlying system is advancing, but the official alert status does not reflect that advance. When the deep process eventually does produce shallow signatures, the transition from low to high alert may need to happen faster than the graduated model anticipates, compressing the preparation time available to communities and the response time available to emergency management agencies. That compression is the specific risk that the current monitoring team is trying to avoid by raising the internal concern level before the shallow confirmation signals have appeared, while the gap between the internal concern and the official alert status creates its own communication challenges. The communication challenge is being navigated in real time through a series of stakeholder briefings that the monitoring agency has conducted in the past week for civil protection authorities, regional governors, and municipal emergency management offices. Those briefings have presented the monitoring data, the range of scientific interpretations, the uncertainty in the timeline, and the specific trigger criteria that would prompt escalation to a higher formal alert level. The purpose of those briefings is not to transfer the scientific uncertainty to the officials who must act under it, but to provide them with sufficient understanding of the uncertainty to make preparedness decisions that are calibrated to the genuine range of possible outcomes, rather than to either the most optimistic or most pessimistic interpretation of the current data. That is a difficult thing to communicate and a difficult thing to receive. Officials making consequential decisions under uncertainty prefer certainty and are not well served by communication that accurately conveys its absence. The monitoring team knows this. The officials know this. The briefings happen anyway, because the alternative, waiting for certainty that may not arrive until the system has already committed to a course that pre-positioned resources could have managed more effectively, is the outcome that everyone in the room is trying to prevent. The public, the 240,000 people in the hazard zone, and the broader population following the news about the elevated monitoring status, is receiving a different communication than the stakeholder briefings provide. The official public statements have been measured, factual, and deliberately non-alarmist. They describe elevated seismic activity at depth, note that the monitoring team is assessing the significance of the signals, confirm that the alert level has not been changed, and recommend that residents in the hazard zone review their emergency preparedness and familiarise themselves with evacuation routes. That communication is not inaccurate. Every sentence in it is true. The aggregate effect of those true sentences, however, is a public message that conveys less urgency than the private discussions happening within the monitoring agency and the Civil Protection Authority. That gap between the internal and public communication postures is a standard feature of volcanic crisis management and reflects a genuine operational judgment that premature escalation of public communication produces response behaviours that are harder to manage than the preparedness deficit it is intended to address. It does not make the gap comfortable, and it does not make the judgment easy to defend if the situation evolves in a direction that the current public communication has not prepared the public to respond to effectively. The residents of the nearest town to the summit, a community of approximately 18,000 people, sitting at the base of the volcano's eastern flank, within the highest hazard zone defined by the current risk assessment, have been through volcanic alerts before. Not a major eruption in living memory for most of them, but smaller episodes of elevated activity, precautionary advisories, and in 2 cases over the past 15 years, temporary evacuation recommendations for specific neighbourhoods closest to the active fumarolic fields on the upper flank. The community has a disaster preparedness committee that has been active since the monitoring agency instituted a community liaison programme 9 years ago. The committee chair, a retired schoolteacher who has been involved in volcano preparedness in the community for most of that 9-year period, received a direct call from the agency's community liaison officer 4 days ago. The call described the current monitoring anomaly in terms that were somewhat more specific than the public statement, acknowledged the uncertainty in the interpretation, and asked the committee to begin a quiet review of the community's current preparedness status without generating unnecessary alarm. That request placed the committee in the same communication tension that the monitoring agency and civil protection authority are navigating at the institutional level, positioned between the scientific reality of genuine uncertainty and the community reality of people who need actionable information to make decisions about their own safety. The committee responded by convening a meeting of the Community Preparedness Network, the web of local officials, community organisation leaders, school principals, health clinic directors, and religious leaders who form the social infrastructure through which official guidance reaches individual households in this community. At that meeting, the monitoring situation was described in terms that matched the call from the agency: uncertain, but warranting enhanced attention. Specific preparedness actions were discussed: confirmation of household go bags with 3 days of supplies, verification of family communication plans, review of the designated community assembly point, and quiet confirmation of which community members have mobility limitations that would require assisted evacuation. Those actions were framed as routine annual preparedness review activities, rather than as crisis response, which is an accurate framing given the current formal alert level, and a communication choice that reflects the committee's judgment about how to maintain awareness without triggering the alarm responses that full crisis framing would produce in a community whose economic life depends significantly on tourism that would be disrupted by any perception of imminent volcanic threat. That economic dimension of the community's relationship to the hazard it lives with is not incidental. The tourism sector in the immediate vicinity of the volcano generates a significant fraction of local employment and business revenue. Restaurants, guest houses, guided hiking operations, souvenir markets, transportation businesses that serve the visitor economy, all of these have a direct economic interest in the perception of the volcano as a manageable backdrop to a tourism experience, rather than an active threat requiring protective action. The business community's relationship with volcanic hazard communication is not uniformly hostile to accurate risk communication, but it is not uniformly supportive either, and the influence of economic interests on the community's response to official hazard messaging has been documented in research on community vulnerability at volcanic tourist destinations globally. It is part of the landscape within which the Preparedness Committee is operating, and within which the monitoring agency's community communication has to find its audience. The seismometers buried in the flanks of the volcano do not know about the tourism economy. They do not know about the Preparedness Committee, or the community briefing, or the gap between public and private communication postures. They record ground motion continuously, 24 hours a day, 7 days a week, and transmit those recordings to the monitoring centre, where they are processed, analysed, and added to the dataset that has been growing for the past 10 days of anomalous activity. The dataset now contains enough observations that the monitoring team's statistical analysis is beginning to produce estimates of the tremor source migration rate with confidence intervals that are narrower than those available from the first few days of data. Those narrower confidence intervals are not pointing in a direction that reduces concern. The central estimate of the upward migration rate, refined against the now larger dataset, remains above the rate that would place the putative intrusion front at the base of the shallow magma storage zone within the coming 3 weeks. The confidence interval around that central estimate is wide enough to include scenarios in which the migration stops or reverses before reaching the storage zone, and wide enough to include scenarios in which it arrives earlier than the central estimate suggests. The central estimate is the best available guess. The confidence interval is the honest description of how reliable that guess is. Both numbers matter. Only the central estimate tends to appear in the summary briefings and public statements. The next 48 hours will be disproportionately important for the trajectory of the scientific assessment. The magnetotelluric survey team has completed deployment of its instrument array and is beginning its first full data collection cycle. The campaign GPS measurements that supplement the permanent network, taken at additional benchmarks not covered by the permanent stations, and providing better spatial resolution of any deformation signal that might be developing, are being processed from the most recent field campaign conducted yesterday. The regular 6-hourly seismic processing continues, and a satellite radar interferometry analysis comparing the most recent satellite radar acquisition of the volcano's surface with acquisitions from 2 and 4 weeks ago is being processed at a remote sensing facility and expected to return results within 36 hours. That interferometry analysis will provide the most sensitive available measurement of any ground deformation that has occurred over the past month at spatial scales and with sensitivity that the permanent GPS network cannot match for subtle, spatially distributed deformation signals. If the interferometry shows deformation, the scientific picture changes substantially. Deformation consistent with pressurization of the shallow magma reservoir would confirm that whatever is happening at depth is connected to the shallow system and would shift the balance of interpretation significantly toward the ascending magma scenario. It would also move the alert level discussion from the current holding pattern to an active escalation consideration within the Civil Protection Authority. If the interferometry shows no deformation above the measurement noise level, it would support the interpretation that the deep signals are not yet, or perhaps are not at all, connected to the shallow storage system, which would be a somewhat more reassuring result without being definitive. The absence of detected deformation does not rule out ascending magma. It constrains the depth and rate of ascent in ways that are useful for the scientific interpretation, but that do not provide the binary clarity that institutional decision-making prefers. The satellite radar acquisition being used for the interferometry was taken under atmospheric conditions that the processing team has assessed as adequate for the analysis, but not ideal. Atmospheric water vapor variations introduce apparent phase changes in radar interferometry that can mimic or mask ground deformation signals if not properly corrected. The processing protocol includes atmospheric correction procedures calibrated against the local atmospheric model, but those corrections are imperfect and introduce uncertainty into the deformation estimate that is larger than the uncertainty from the radar measurement itself. The final deformation result will carry an uncertainty estimate that reflects both the measurement noise and the atmospheric correction uncertainty. Whether that combined uncertainty is small enough to confidently detect or rule out the level of deformation expected from a new magmatic intrusion at the depth inferred from the seismic analysis depends on the magnitude of the deformation, which in turn depends on the volume and pressure of the intruding material, which is precisely what is not known. The analysis is being conducted at the intersection of multiple unknowns, using measurement precision that is remarkable by the standards of 20 years ago, and that remains imperfect relative to the discrimination required. 20 years ago, this analysis would not have been possible. The satellite radar constellation that makes interferometric monitoring of volcanic deformation a routine operational tool did not exist 2 decades ago in its current form. The computational infrastructure for processing the large data volumes involved did not exist. The interpretive frameworks developed from the now extensive library of case studies of volcanic deformation observed by satellite radar did not exist. The volcanic monitoring landscape has been transformed in the past 2 decades by exactly this kind of technical innovation, by the combination of better satellite coverage, better computational tools, better geophysical modelling, and better integration of multiple measurement types into coherent multi-parameter assessments. The transformation has improved forecast capability at well-monitored systems substantially. It has also raised the bar for what constitutes adequate monitoring at systems that receive less attention, creating a growing divide between the handful of volcanoes with comprehensive multi-parameter networks and the majority of the world's approximately 1,500 potentially active volcanoes that are monitored at much lower levels of resolution and continuity. The world's approximately 1,500 potentially active volcanoes represent a hazard that is distributed unevenly across the planet and that falls disproportionately on the populations of developing nations in tropical and island settings where volcanic systems are prevalent and where monitoring capacity is most limited. The disproportion is not coincidental. The same geographic and tectonic factors that produce active volcanic systems, subduction zones, oceanic hotspots, continental rift zones, also tend to produce the kinds of geological environments that support island and coastal ecosystems whose human populations developed in relationship to the volcanic landscape they inhabit. The people living in the shadow of the world's less monitored volcanoes are not there by accident. They are there because the volcanic soils are fertile, because the coastal settings supported fishing economies, because the landscapes that volcanoes create are beautiful and resource-rich in ways that have attracted and supported human settlement for thousands of years. The same geological productivity that creates volcanic hazard creates the conditions that have brought people to live within its reach. Addressing the monitoring gap at the world's inadequately observed volcanic systems is a recognised priority in the international volcanological community and has been identified as such in multiple assessment reports from the United Nations Office for Disaster Risk Reduction and the World Meteorological Organization. The practical progress on addressing that gap has been modest relative to the scale of the problem, for the familiar combination of reasons that attend any global public goods problem. The volcanoes most in need of better monitoring are predominantly in countries with the most limited resources to fund monitoring programs. International funding for volcanic monitoring capacity building has grown in recent years, but remains a small fraction of what would be required to bring all potentially active systems to a monitoring standard comparable to the best observed systems. Satellite-based monitoring has partially addressed the gap by providing synoptic coverage of deformation and thermal emission at volcanoes without ground-based instrumentation. But satellite monitoring without ground truth from local sensor networks and field measurements cannot achieve the interpretive resolution that the current situation at this well-monitored system is still struggling to provide. The gap between what is known and what needs to be known to confidently characterize the hazard at this well-monitored volcano is the honest measure of how much further the science needs to advance before volcano monitoring can provide the certainty that hazard management demands. That gap exists here at one of the best observed volcanic systems on the planet, with decades of baseline data, a sophisticated multi-parameter network, and an engaged scientific community providing real-time analysis support. At the thousands of volcanic systems without those advantages, the gap is immeasurably larger. The consequences of that larger gap, when those less monitored systems produce major eruptive episodes, have been written repeatedly in the historical record and will be written again. The historical record of major volcanic eruptions in the past 2 centuries includes events that reshaped regional climates, disrupted global food systems, and killed tens of thousands of people in hours. It also includes events at well-monitored volcanoes where comprehensive warning systems functioned as designed and where the human cost was dramatically lower than the geological potential of the eruption would have allowed. The 1991 eruption of Mount Pinatubo in the Philippines, the second largest volcanic eruption of the 20th century, was preceded by a monitoring campaign that detected the precursory signals sufficiently in advance to allow the evacuation of approximately 60,000 people from the highest hazard zones. The eruption produced pyroclastic flows, ashfall, and lahars that would have killed tens of thousands of additional people had those evacuations not occurred. The death toll was approximately 800, a number that represents genuine tragedy and that is simultaneously a fraction of what it would have been without the monitoring and warning system that functioned in the months preceding the eruption. Pinatubo is the case study that the international volcanological community returns to most consistently when making the argument for investment in volcanic monitoring, because it demonstrates in the clearest possible terms what the return on that investment looks like when the science works and the institutions respond. The current situation at this volcano is not Pinatubo. The signals are different, the depth is different, the timeline is different, and the scientific interpretation is genuinely uncertain in ways that the Pinatubo precursor sequence, in retrospect, was not. The current situation is something less defined and in some ways more difficult to manage, precisely because it lacks the clarity that made the Pinatubo response possible. It is the kind of situation that the science of volcano monitoring has been advancing toward the ability to handle with confidence and has not yet fully achieved. It is a situation being managed by capable professionals using the best available tools in conditions of genuine uncertainty, trying to protect a population that does not yet know it may need protecting against a hazard that may or may not materialize on a timeline that cannot yet be specified. The instruments keep recording, the data keeps arriving, the scientists keep analyzing. The ground under the volcano keeps doing whatever it is doing, 35 kilometers below the surface, beyond direct observation, revealing itself only through the proxy signals that reach the sensors at the surface and travel through the processing chain to the workstations, where the monitoring team is trying to read what the mountain is trying to say. The mountain has been saying something for 10 days. The people whose job is to listen have not yet agreed on what it means. That disagreement is not a failure. It is the honest condition of science operating at the edge of what current knowledge and current instrumentation can resolve. The resolution will come. It will come either from the geological process itself, as the subsurface evolution produces signals clear enough to discriminate between the competing interpretations, or from the additional observations being mobilized in response to the current anomaly, or from some combination of both. When the resolution comes, the monitoring team will communicate it. The Civil Protection Authority will act on it. The communities in the hazard zone will respond to it. Until then, the mountain waits, and the instruments record. And 35 kilometers below the surface, something moves through rock that has not been disturbed in decades, following pathways carved by the same geological forces that built the mountain above it, carrying heat from a depth that most people will never think about, toward a surface where 240,000 people are going about their lives in the shadow of something that has not yet decided what it is going to do. The something moving through rock 35 kilometers below the surface has a name in volcanology, though the name is more a label for a process than a description of a discrete object. It is called a magmatic intrusion, which sounds clinical and contained, like a medical procedure, like something that happens in a controlled environment with defined boundaries and predictable outcomes. It is none of those things. A magmatic intrusion is a volume of partially molten rock under pressure, moving through pre-existing fractures or creating new ones, following the path of least resistance through a medium that is simultaneously solid enough to fracture and hot enough to deform plastically, depending on the timescale of the stress being applied. Its boundaries are not sharp. Its edges grade from molten material at the center into a zone of partial melt, into a zone of hot but solid rock that has been thermally altered by proximity to the melt, and then into the surrounding country rock that is being heated, stressed, and fractured by the intrusion's advance. The seismic sensors recording the low-frequency tremors are detecting the acoustic emissions of that fracturing, of fluid moving through fractures that the intrusion is opening, of the thermal cracking of rock being heated faster than it can expand without breaking. The signals are the sound of the mountain's interior being rearranged. That rearrangement has a direction, it has a velocity, it has a volume, though that volume is one of the least constrained parameters in the current assessment, because the relationship between seismic signal amplitude and intrusion volume depends on assumptions about the rock properties and fluid content of the source region that the monitoring network cannot independently verify. The direction is upward, constrained by the progressive shallowing of the tremor source locations over the 10-day observation window. The velocity is estimated, with the uncertainty already described, from the rate of that shallowing. The volume is bracketed by the physical arguments about what volumes of ascending magma are capable of producing the observed signal amplitudes, without producing other signals that have not been observed, a negative constraint that is logically valid and practically useful, and that still leaves a range spanning nearly an order of magnitude between the minimum and maximum plausible intrusion volumes consistent with the dataset. An order of magnitude in intrusion volume is the difference between an intrusion that reaches the shallow storage zone and stalls, adding incrementally to a magma reservoir that may not be critically pressurized, and an intrusion that delivers a large enough volume of fresh, gas-rich magma into the storage zone to push it over the pressure threshold that initiates eruptive activity. The eruption threshold is not a fixed physical constant. It depends on the pre-existing state of the magma reservoir, on how much gas is already dissolved in the resident magma, on the mechanical strength of the overlying rock that must fracture to allow magma to reach the surface, and on whether any pathways from the reservoir to the surface are already partially open from previous eruptive episodes. All of those parameters have values at this specific volcano that are known imperfectly from the combination of geophysical imaging, geochemical sampling of volcanic products, and the record of previous eruptive behavior. The imperfect knowledge of those parameters propagates into imperfect knowledge of the eruption threshold, which propagates into imperfect ability to predict whether a given intrusion volume will or will not exceed it. The research literature on magma reservoir dynamics has advanced substantially in the past decade through the combination of improved geodetic monitoring, experimental petrology, and numerical modelling of magma-crust mechanical interaction. The current understanding of how magma reservoirs fail, of what processes bring a volcanic system from a state of recharge to a state of eruption, is considerably more sophisticated than it was 20 years ago. It is also considerably more honest about the complexity of the process and the degree to which that complexity limits deterministic prediction. The simple conceptual model of a magma chamber filling like a balloon until it pops has been replaced by a more nuanced picture of a complex, heterogeneous, partially molten zone occupying a significant fraction of the lower crust, with melt distributed through a crystal-rich mush that responds to new magma input through a combination of mechanical pressurization, chemical reactivation of crystallized material, and thermal rejuvenation of regions that had cooled below their solidus temperature. That mush system can absorb considerable amounts of new magma input without erupting, accommodating the volume increase through deformation and partial remelting of the crystal matrix. It can also, under the right conditions of input rate, input temperature, and pre-existing mush state, transition relatively rapidly from quiescent storage to active mobilization, producing the kind of accelerating precursory signal sequence that ends in eruption. The transition from quiescent storage to active mobilization is the process that every volcanic monitoring program is trying to detect before it completes. Detection before completion requires identifying the signals of mobilization in their early stages, when the changes in the mush system are still subtle, and when the observational signatures at the surface are ambiguous between mobilization and non-eruptive recharge. The monitoring tools available today are sensitive enough to detect those early signals at well-instrumented systems. The interpretive frameworks for distinguishing mobilization signals from non-eruptive recharge signals are not yet mature enough to make that distinction reliably in real time, which is precisely the situation the current monitoring team faces. They can see that something is changing. They cannot yet confidently say whether what is changing is the slow recharge of a system that will remain quiescent for years, or the initial stages of a mobilization that will eventually produce an eruption. The word "eventually" is doing significant work in that sentence. Eventually could mean weeks, it could mean years, it could mean decades. The timescale from the onset of detectable deep recharge to the occurrence of an eruption varies by orders of magnitude across different volcanic systems and different eruptive episodes at the same system. Some volcanic systems produce eruptions within days to weeks of the first detectable precursory signals. Others show persistent recharge activity for years or decades before erupting. The historical record at this specific volcano includes both short-duration and long-duration precursory sequences, though the record is incomplete enough that the distribution of pre-eruptive timelines cannot be quantitatively characterized with high confidence. The monitoring team's current probabilistic assessment of the timeline to a potential eruption, if an eruption occurs, is not a number that the public statements have communicated, and is not a number that the monitoring team is fully comfortable assigning, because the uncertainty in that number is large enough that communicating it as a specific probability would convey more false precision than genuine information. False precision in hazard communication is a specific failure mode that the risk communication research community has documented extensively. It occurs when quantitative probability estimates are presented in formats that suggest greater confidence than the underlying analysis supports, leading recipients to update their mental models more strongly than than the quality of the evidence warrants. In the context of volcanic hazard communication, false precision manifests as eruption probability estimates presented as specific percentages, when the uncertainty in those estimates spans ranges that would be described as very wide if honestly characterized. A statement that there is a 30% probability of an eruption in the next 30 days sounds precise and actionable. If the honest uncertainty range around that 30% spans from 5% to 70%, the statement is conveying a false sense of the confidence with which that central estimate is held. The person receiving the 30% figure and using it to make a decision about whether to evacuate their home is making that decision based on a number whose true uncertainty would, if honestly conveyed, suggest a much wider range of possible actions might be defensible. The alternative to false precision is honest uncertainty communication, which faces its own failure modes. Communicating uncertainty honestly often produces in recipients the cognitive response of discounting the entire message, interpreting the acknowledgement of uncertainty as evidence that the experts do not really know anything useful and that the warning can safely be ignored. Research on this phenomenon, sometimes called uncertainty paralysis, has shown that the way uncertainty is framed matters enormously for whether recipients use it to make better decisions or use it as a reason to make no decision at all. Uncertainty framed as a range of plausible outcomes, with the consequences of each outcome clearly described, tends to support better decision-making than uncertainty framed as imprecision in a single probability estimate. The communication that the monitoring agency has been providing in its stakeholder briefings attempts to use the scenario-based framing, describing the range of possible trajectories and the observable signatures that would indicate the situation is moving toward the more concerning end of the range. Whether that approach is reaching the public through the translation layer of official statements and media coverage with its intended structure intact is a question the agency cannot easily answer from inside its own communication process. The media coverage of the current situation has been shaped by the official communication posture, which is measured and non-alarmist, and by the journalistic incentives that pull in the direction of dramatic framing. Those two forces have produced coverage that is generally accurate in its individual factual claims, and that creates, in aggregate, an impression that is slightly more alarming than the official statements alone would suggest, but considerably less specific than the internal scientific assessment would support. The newspaper headlines reference unusual seismic activity and scientists on alert without conveying the specific character of the deep tremors or the reasons that their depth and spectral character distinguish them from the routine background seismicity that every volcanic system produces. The television news segments show footage of steam venting from the summit, which has been occurring continuously for years and is unrelated to the current anomalous signals, alongside graphics of the volcano's eruption history that provide visual drama without analytical context. The online coverage includes a range of quality, from reasonably detailed science journalism to speculation about imminent catastrophe that bears no relationship to the current scientific assessment. The range of online coverage reflects a broader challenge in science communication that volcanic hazards share with other complex geophysical risks. The internet has dramatically democratized access to information about scientific topics, while simultaneously creating a media environment in which the quality of information and the credibility of sources are difficult for non-specialists to evaluate. A person searching for information about the current volcanic situation will encounter the official monitoring agency's measured technical bulletins, alongside blog posts from amateur volcano enthusiasts whose enthusiasm exceeds their interpretive expertise, alongside coverage from regional news organisations with varying levels of science journalism capacity, alongside social media posts from individuals near the volcano reporting their personal observations with varying degrees of accuracy and context. Navigating that information landscape to form an accurate understanding of the current hazard requires exactly the kind of scientific background that most people do not have, and that no single communication product from the monitoring agency can substitute for. The monitoring agency has a public communication team that manages its website, social media presence, and media relations, alongside the scientific monitoring operation. That team has been in a state of elevated activity for the past 10 days, managing a volume of media inquiries significantly above the baseline, coordinating the official statements with the Civil Protection Authority, and attempting to provide context for the monitoring data that goes beyond the bare numbers in the technical bulletins. The public communication team's challenge is the same challenge in a different register as the science team's challenge in the internal briefings. How do you convey genuine uncertainty in a way that supports appropriate preparedness action without either minimizing the risk or amplifying it beyond what the data supports? The team members who have been doing this work for years have developed a practice of describing what the instruments are showing, what the range of interpretations is, and what the observable signs of escalation would be, rather than summarizing the situation in a single characterization that inevitably either understates or overstates the complexity. That practice is more informative than a simple reassuring or alarming summary. It is also more cognitively demanding of the recipient and produces less satisfying soundbites for media coverage that operates on shorter attention spans. The attention span problem is not a new observation about media and science communication. It has been described, lamented, and partially addressed by practitioners in every domain of complex technical risk communication for decades. What is new is the speed at which information circulates in the current media environment, which compresses the timeline between the occurrence of a noteworthy development and the appearance of media coverage of it from hours to minutes. That compression has reduced the time available for the translation layer to function, for the monitoring agency's communication team to craft a response that accurately contextualizes a new data point before that data point has already been interpreted, decontextualized, and shared widely through informal channels. The low-frequency tremors that initiated the current assessment first appeared in the public discourse, not through an official agency communication, but through a social media post by a seismology enthusiast who had noticed the signal in the publicly accessible real-time seismogram feed that the monitoring agency maintains as part of its transparency commitment. That post circulated widely among people interested in volcanic activity before the agency had issued any official statement, creating a period during which the signal was being discussed publicly in the absence of the interpretive context that the agency's communication team was still preparing. The agency's first public statement, issued several hours after the social media discussion had begun, was responding to a situation that had already been partially framed by informal communication it had no control over. That dynamic, monitoring agencies finding themselves in a reactive posture relative to informal public discussion of their own data, is increasingly common in an era when raw data from monitoring networks is routinely made publicly accessible in real time as part of transparency and open science commitments. Those commitments are scientifically and democratically valuable. The data belongs to the public that funds the monitoring programs. Making it accessible enables independent analysis, supports scientific research, and builds the public familiarity with volcanic monitoring that improves community preparedness over the long term. The trade-off is the loss of the agency's ability to control the timing of public awareness of notable data features, which in practice means the agency sometimes finds itself explaining data that has already been interpreted by people without the interpretive expertise to contextualize it accurately. Managing that trade-off is an ongoing challenge for monitoring agencies globally, and one for which no fully satisfying solution has been identified, because the alternative of restricting data access to prevent premature public discussion conflicts with the transparency values that make the monitoring data publicly valuable in the first place. The publicly accessible seismogram feed that revealed the initial anomalous tremors to the social media community continues to show those tremors in real time. Anyone with internet access and a browser can watch the ground motion record from the monitoring stations as it is produced, scrolling across the display in the familiar waveform traces that seismologists read the way musicians read notation. The tremors appear as sustained oscillations at frequencies below the range of most earthquake-generated signals, distinguishable to a trained eye from the sharp, impulsive arrivals of tectonic earthquakes and from the high-frequency noise of wind, traffic, and human activity that contaminates the surface sensor records. To an untrained eye, they look like something is happening. That impression is correct. Whether that something is the specific thing that would justify alarm is the question that trained eyes are still debating. The debate has a geographical dimension that adds a layer of complexity to the communication challenge. The scientific community engaged with the current assessment is not physically located in one place. The local monitoring team is on site, managing the network and the institutional relationships with civil protection authorities and community stakeholders. International collaborators are distributed across multiple time zones, engaging through video calls, shared data repositories, and email exchanges that produce asynchronous discussions at the pace of human communication rather than at the pace of the evolving geological situation. The synthesis of those distributed contributions into a coherent scientific assessment that the local team can act on and communicate requires coordination that adds latency to the decision-making process. A new data point arriving at the local monitoring centre at midnight local time can be incorporated into the local team's assessment within hours. Incorporating the input of international collaborators in different time zones may take an additional 12 to 24 hours, depending on when those collaborators are available and how quickly the discussion converges. In a situation evolving on a timescale of days to weeks, that latency is manageable. In a situation that shifts abruptly toward rapid escalation, it could become significant. The contingency planning for a rapid escalation scenario is one of the topics that the monitoring team and the Civil Protection Authority have been reviewing in the past week. Rapid escalation, defined for planning purposes as a transition from the current anomalous but non-eruptive state to clear pre-eruptive shallow signals within a period of days rather than weeks, would compress the decision timeline in ways that the standard graduated response model does not fully accommodate. The planning review has identified several decision nodes where the time available for deliberation under a rapid escalation scenario would be shorter than the standard protocol assumes, and has pre-authorized specific response actions at those nodes to reduce the decision latency if the situation evolves rapidly. Pre-authorization of response actions, the agreement in advance that certain observable monitoring thresholds will automatically trigger certain response actions without requiring additional deliberation, is a planning approach that trades flexibility for speed. The trade-off is generally favorable in rapidly evolving hazard situations, where the cost of delayed response exceeds the cost of occasional premature response. It requires confidence in the trigger criteria, confidence that the observable thresholds being used as automatic triggers are reliable indicators of the hazard state they are intended to signal. Building that confidence is itself a scientific task that the monitoring community has been working on for years. The trigger criteria under review in the current planning context include the appearance of shallow seismicity above a defined rate threshold, ground deformation above a defined magnitude threshold on the GPS network, a defined step change in sulfur dioxide flux at the summit fumaroles, and the appearance of hybrid earthquakes at shallow depths whose waveform characteristics indicate brittle fracture of rock immediately above the magma storage zone. Those are the shallow confirmation signals that the deep tremors have not yet produced. Their absence is the current state. Their appearance, if it occurs, is what the pre-authorized response protocols are designed to trigger. The monitoring team has reviewed the sensitivity and specificity of each criterion against the historical record of eruptive and non-eruptive episodes at this and comparable volcanic systems, and has made adjustments to the threshold values to reduce both false positive and false negative rates relative to the previous protocol version. The adjustments represent genuine scientific improvement in the trigger criteria. They are not perfect. They will produce some false positives, some escalations triggered by signals that do not progress to eruption, and potentially some false negatives, some episodes where the observable signatures of genuine escalation do not trip the specified thresholds in the expected order or at the expected rates. The goal of the protocol review is to make the criteria as reliable as the current scientific understanding allows, while building in enough redundancy across multiple independent indicators that the overall protocol is less likely to fail catastrophically than any individual criterion within it. The redundancy principle is fundamental to reliable system design in any domain involving consequential decisions under uncertainty. Aviation safety, nuclear power plant operations, and medical diagnostics all employ redundant indicator systems precisely because no single measurement is fully reliable and the consequences of system failure are severe enough to justify the cost of multiple independent monitoring channels. Volcanic monitoring has adopted the redundancy principle through the multi-parameter approach that the current system embodies. No single indicator, neither the seismic data nor the deformation data, nor the gas data, nor the thermal data, is treated as definitive in isolation. The assessment is based on the pattern across multiple independent indicator systems, and the trigger criteria in the escalation protocol require corroboration from multiple channels before the highest level response actions are initiated. That redundancy provides protection against false alarms triggered by instrument failures or transient non-volcanic signals affecting a single monitoring channel. It also means that a genuine pre-eruptive sequence that, for whatever reason, does not produce the expected multi-channel corroboration pattern may not trigger the protocol thresholds, even if individual channels are showing concerning signals. The protocol is designed around the expected pattern. Unexpected patterns require human judgment to override the protocol's automatic logic, and human judgment under time pressure in an unfamiliar situation is exactly the scenario where cognitive biases and institutional pressures produce the worst outcomes. The worst outcomes in volcanic crisis management have often been associated with exactly that scenario, with situations where the observable signals did not match the expected pre-eruptive pattern, and where the human judgment that had to fill the interpretive gap was compromised by time pressure, by institutional dynamics, by communication failures, or by the simple cognitive difficulty of updating a risk assessment when new information is ambiguous and the consequences of being wrong in either direction are severe. The literature on volcanic disaster case studies, from the Nevado del Ruiz Lahar to the Soufriere Hills eruption in Montserrat that displaced 2/3 of the island's population, to the ongoing crisis at Campi Flegrei in Italy, where ground uplift has been accelerating in a densely populated caldera for years, is a literature about the human dimension of volcanic risk as much as the geological dimension. The geology produces the hazard. The human response to the hazard determines the outcome, and the human response is shaped by all of the factors that have been discussed in the context of this current situation. The quality of the monitoring, the clarity of the scientific assessment, the effectiveness of the communication, the institutional capacity and political will to act on that communication, the economic and social circumstances of the populations at risk, and the individual decisions made by people who are trying to protect their lives and livelihoods under conditions of genuine uncertainty. Campi Flegrei deserves particular attention in this context because it represents the most extensive ongoing volcanic crisis management situation in the world, and because it presents, in acute form, the specific challenge of managing a large, partially urbanized caldera system whose activity has been escalating in ways that the monitoring community can characterize but cannot yet confidently interpret as eruptive versus non-eruptive. The Campi Flegrei caldera sits on the western edge of Naples, Italy, and encompasses a densely populated area including the city of Pozzuoli and numerous smaller communities with a combined population of approximately 500,000 people within the zones of highest hazard. The caldera has been in a state of bradyseism, the cyclical rise and fall of the ground surface associated with fluctuating magmatic and hydrothermal activity at depth, for decades. The current episode of ground uplift, which began in approximately 2005, has now produced more than 1 metre of net uplift at the centre of the caldera, with the rate of uplift accelerating in the most recent years and the accompanying seismicity increasing in both rate and maximum magnitude. The Italian National Institute of Geophysics and Volcanology, which operates the monitoring network at Campi Flegrei, has raised the alert level for the caldera twice in recent years and maintains an active research and monitoring program that is among the most intensive applied to any volcanic system in the world. The situation at Campi Flegrei is different from the current volcano in important ways. The caldera is larger, the population at risk is larger, the geological history is more complex, and the potential eruption scenarios span a wider range, from relatively small vents producing limited lava flows and ash, to large explosive eruptions that caldera systems are capable of generating on longer timescales. The monitoring challenge is different because the activity is distributed across the caldera rather than focused at a single edifice, and because the hydrothermal system, which is unusually large and energetically active, contributes signals that are difficult to decompose from the deeper magmatic signals the monitoring network is trying to characterize. But the fundamental challenge is the same: a system that is doing something new, that has never produced a major eruption in recorded history, that sits above a large and economically important urban population is showing escalating activity that the scientific community cannot yet confidently characterize as progressing toward eruption or not. The decisions being made in Italy about how to manage preparedness for a potential eruption at Campi Flegrei, about how to communicate the hazard to 500,000 people, about how to develop and maintain viable evacuation plans for a population that is not uniformly willing to accept the reality of the hazard it lives with, are being watched by volcanic hazard managers around the world, including the team at the current Volcano, as a case study in managing exactly the kind of uncertainty that they are currently navigating at their own system. The watching goes in both directions. The Italian researchers managing Campi Flegrei are watching the current volcano's anomalous deep tremors and the monitoring team's response to them. Every volcanic crisis at a well-monitored system produces observations and lessons that the global community absorbs and applies to its own monitoring challenges. The deep tremor source location technology being used to track the apparent migration of fluid sources at the current volcano incorporates algorithms and processing approaches developed partly through work on deep, low-frequency seismicity at several other subduction zone volcanoes in the Pacific and in Central America. The gas monitoring protocols, the GPS network design, the satellite radar analysis procedures, all of these draw on a global scientific commons of methods and knowledge that has been built through the accumulated experience of monitoring programs at dozens of volcanic systems over decades. The return contribution from the current situation, whatever its outcome, will add to that commons in ways that the monitoring team cannot fully anticipate, but that future monitoring programs at comparable systems will benefit from. The benefit to future monitoring programs is not the immediate concern of the 240,000 people in the current hazard zone. Their concern is more immediate and more personal. It is the concern of people trying to understand what the information they are receiving means for decisions they need to make about their families, their property, and their livelihoods. The Preparedness Committee chair in the town of 18,000 people on the eastern flank made a second call to the agency's community liaison officer yesterday. The call was about a specific, practical question. The community's designated evacuation assembly point, a large public parking area on higher ground, approximately 3 kilometers from the town centre, has a capacity based on the current population distribution in the town and surrounding area that the Preparedness Committee now believes may be inadequate given recent population growth in areas closer to the higher hazard zones on the lower flanks. The committee has identified an alternative secondary assembly point with additional capacity, but wants the agency's assessment of whether that secondary site is itself within the hazard zone for certain eruption scenarios before committing to incorporating it into the community preparedness plan. That call represents exactly the kind of practical, specific, operationally consequential interaction between the monitoring agency and community stakeholders that the agency's Community Liaison Programme was designed to support. The answer to the Preparedness Committee's question requires the agency to provide not just a general characterisation of the hazard zone, but a site-specific assessment of whether the proposed secondary assembly point falls within the simulated flow paths for any of the eruption scenarios in the current hazard model. That assessment is being generated from the agency's Geographic Information System using the modelled flow path data from the most recent hazard analysis. It will be delivered to the Preparedness Committee within 24 hours. The assembly point question may seem like a logistical detail compared to the larger questions about what is happening 35 kilometres below the surface. It is not a detail. It is the specific link between the abstract hazard assessment and the concrete preparedness action that would protect a specific group of people in a specific location if the hazard materialises. Getting it right matters as much as getting the seismic interpretation right, because the seismic interpretation only saves lives if the preparedness infrastructure built on it is adequate to the task. The preparedness infrastructure being built and refined in response to the current monitoring anomaly extends beyond the community level to the regional logistics of a potential large-scale evacuation. Moving 240,000 people out of a volcanic hazard zone requires transport capacity, route management, reception centre capacity, fuel supply, and coordination among dozens of agencies and jurisdictions that in normal times have no operational relationship with each other. The Regional Civil Protection Authority has been conducting a quiet audit of the current state of that infrastructure, assessing where gaps exist between the documented capacity and the actually available capacity that would materialise in a real mobilisation. Documented capacity is what exists on paper. Actually available capacity is what would be present on the ground when the mobilisation order goes out at 3 a.m. on a Tuesday in the middle of the growing season, when the roads are already carrying agricultural traffic and the fuel depots are at their seasonal low. The gap between documented and actually available capacity is a consistent finding in post-event analyses of large-scale evacuation operations globally. Most plans look better on paper than they perform in execution because the frictions and failures that real-world mobilisations inevitably encounter are not fully captured by the planning models. The audit is finding gaps. That is not surprising. It would be more surprising if it found no gaps, given the time elapsed since the last major preparedness review and the changes in the regional population distribution, road network, and reception centre inventory that have occurred in the intervening years. The gaps being identified fall into several categories. Transport capacity for mobility-limited individuals is the most significant, as it is in most large-scale evacuation planning assessments, because the people who need the most assistance in an evacuation are the ones whose needs are hardest to quantify in advance and who require the highest ratio of resources per person moved. Medical support capacity at reception centres for people with chronic conditions requiring regular medication or treatment is a close second. Communication infrastructure for maintaining contact with people who have evacuated and need ongoing information about the situation and about when, if ever, it is safe to return is a third. Each of those gaps has a potential remediation action, and each remediation action has a cost and a timeline for implementation. The Civil Protection Authority is prioritising the remediation actions by the combination of gap severity and implementation feasibility, trying to identify the actions that can be completed within the current warning timeline and that would produce the greatest reduction in response risk if the situation escalates to requiring full mobilisation. The current warning timeline, the period between now and the point at which the monitoring signals might be expected to provide more definitive guidance on the hazard trajectory, is estimated at 2 to 4 weeks based on the current rate of apparent intrusion migration and the depth remaining before the putative intrusion front reaches the base of the shallow storage zone. That estimate is the central tendency of a distribution whose tails extend in both directions. On the shorter end, an acceleration of the intrusion rate could reduce the timeline to days. On the longer end, a deceleration or cessation of the deep activity could extend the period of uncertainty indefinitely. Planning for the central estimate, while maintaining contingency for the short end tail, is the operational posture the Civil Protection Authority has adopted. Maintaining contingency for the short end tail means having the highest priority preparedness gaps remediated before the end of the current week, which is an aggressive target given the resources available and the normal pace of government logistics. It is a target that the Civil Protection Authority has made as a commitment to the monitoring agency in the Joint Planning Review. Whether that commitment will be met depends on factors including procurement lead times, contractor availability, and the pace of bureaucratic approvals for emergency expenditures that do not yet have the formal designation of a declared emergency to accelerate them. The absence of a formal emergency declaration is itself a governance issue that the current situation illuminates. Emergency declarations in most governmental systems unlock expedited procurement, override normal budget authority constraints, and activate mutual aid agreements with neighbouring jurisdictions that provide access to resources not available from within the declaring jurisdiction alone. They also carry costs beyond the financial. A formal emergency declaration signals to the public that the situation has passed a governmental threshold of concern that routine monitoring communications do not. It changes the community response in ways that can be both beneficial, increasing preparedness action and attention to official guidance, and problematic, accelerating the economic impacts on tourism and agriculture that communities near volcanoes depend on, and that early declarations can trigger prematurely if the hazard ultimately does not materialise. The Civil Protection Authority has not declared a formal emergency. It has instead been operating in the procedural space between normal operations and formal emergency designation, using informal authorities and pre-positioned resources to advance preparedness without triggering the full cascade of formal emergency mechanisms. That procedural space is useful precisely because it allows preparedness action faster than normal government processes permit, while avoiding the full social and economic costs of a formal emergency declaration. It is also a space that is not unlimited in its availability, a space that becomes increasingly untenable as the situation evolves, and the gap between the informal preparedness actions being taken and the formal status of the situation becomes harder to explain to the public and to elected officials who are being asked questions they cannot answer without reference to a formal status designation. The elected officials at the regional and municipal levels, whose jurisdictions include the hazard zone communities, are navigating their own version of the communication challenge. They are receiving briefings from the Civil Protection Authority that provide more detail than the public statements. They are being asked by constituents for clarity that the situation does not yet permit. They are making public statements that try to balance honest acknowledgement of the monitoring anomaly with reassurance that does not undermine preparedness action, a balance that is inherently difficult to maintain, and that different officials are striking differently based on their individual communication styles, their political situations, and their judgments about what their constituents need to hear. The variation in official public communication across the different jurisdictions affected by the current monitoring anomaly is creating a confusing landscape for residents trying to understand whether what they should be doing in their specific community is the same as, or different from, what residents in neighbouring communities are being told. Consistency in public messaging across jurisdictions is a recognised challenge in multi-jurisdictional hazard communication and is one of the specific coordination tasks that regional civil protection frameworks are designed to address. The current framework is addressing it imperfectly, as multi-stakeholder coordination in real-time evolving situations almost always does. The real-time evolution of the situation is being tracked by the monitoring team through its continuous data streams, and by the international scientific community through the shared data and periodic technical briefings that the monitoring agency is conducting with its international partners. The most recent technical briefing, conducted via video conference 36 hours ago, included participants from 9 countries and produced a discussion that lasted 3 hours and ended, as such discussions tend to, when the data is genuinely ambiguous, without consensus on the central interpretive question. The participants agreed that the signals are real, that they are anomalous relative to the established background, and that they warrant the current level of enhanced monitoring and preparedness review. They did not agree on whether the signals represent the early stages of a new magmatic episode or a non-eruptive hydrothermal response to deep crustal stress changes. They did not agree on the probability of escalation within the next 4 weeks, and they did not agree on the specific observational signatures that would be most diagnostic in distinguishing between the competing interpretations, though they identified several candidates that the local team is now prioritising in its analysis. The candidates for diagnostic observations include the polarisation characteristics of the tremor waveforms, which carry information about the geometry of the source mechanism that standard tremor location analysis does not capture, and that might help distinguish between fluid migration through a crack-like fracture system, consistent with the hydrothermal interpretation, and fluid migration through a more pipe-like conduit structure, more consistent with a magmatic pathway. Extracting polarisation information from the existing borehole seismometer array requires reprocessing the raw waveform data with an analysis approach that has not been applied to this dataset before. That reprocessing is underway and is expected to produce initial results within 48 hours. The results will be preliminary, subject to revision as the analysis methodology is refined, and will carry uncertainty that may or may not be small enough to discriminate between the competing source geometries. But they represent the best available use of the existing dataset beyond what has already been extracted, and the effort to extract additional information from data that is already in hand is both scientifically appropriate and operationally important in a situation where additional observational data is constrained by the logistics and time requirements of field deployment. The field team that has been deploying additional seismometers around the volcanic edifice since the onset of the anomalous activity has completed installation of 6 new stations at positions designed to improve the 3-dimensional resolution of deep source locations. Those stations came online in staggered sequence over the past week, with the most recent installation completed 2 days ago. The complete array, combining the original borehole network with the new surface stations, is now providing source location estimates with spatial uncertainty roughly 40% smaller than the estimates available from the original network alone. That improvement in location precision is already revealing subtle spatial structure in the tremor source distribution that the original network could not resolve. The sources are not uniformly distributed through the lower crust. They cluster preferentially along what appears, in the current three-dimensional visualization, to be a subvertical zone of enhanced seismic activity that aligns roughly with the known geometry of a fault system that has been imaged in previous seismic surveys of the volcano's crustal structure. That alignment is consistent with fluid migration along a pre-existing structural weakness in the crust, which is physically expected since ascending fluids preferentially exploit existing pathways rather than creating new ones, except when the driving pressure is sufficient to fracture intact rock. The fault alignment does not resolve the interpretive question of whether the ascending fluids are magmatic or hydrothermal in origin, but it provides a structural context for the deep activity that the previous location estimates, with their larger uncertainties, could not clearly establish. And it adds a geometrically coherent picture to the dataset that will inform both the ongoing scientific interpretation and the hazard modelling for potential future scenarios. The hazard modelling for potential future scenarios is being updated in parallel with the scientific interpretation effort. The current hazard model was last formally revised following the most recent major eruption cycle and represents the state of knowledge at the time of that revision. Since then, advances in numerical modelling of volcanic flow processes, in the resolution of the digital elevation model used for flow path simulation, and in the understanding of the volcano's shallow plumbing system from the geophysical surveys conducted in the intervening years, have collectively produced a basis for model improvements that the monitoring agency has been planning to implement in the next scheduled model revision. The current anomalous activity has accelerated that schedule. The revised model, incorporating updated flow simulation parameters and the more recent topographic data, is expected to produce hazard zone boundaries and inundation depth estimates that differ in important respects from the current version. In some areas, the revised boundaries will expand, incorporating terrain that the previous model showed as outside the primary impact zones, but that the updated topographic data and revised flow simulation parameters suggest may receive significant deposits in certain eruption scenarios. In other areas, the boundaries may contract, where the updated model shows that terrain features, drainages or ridges, or elevated road embankments that were poorly resolved in the earlier topographic dataset would channel flows away from areas that the previous model included in the hazard zone. The practical consequence of hazard zone boundary revisions during an active monitoring anomaly is a communication challenge of a specific character. People who were outside the previous hazard zone boundaries and are now inside the revised ones need to be informed of their changed status. People who were inside the previous boundaries and are now outside the revised ones need to be told that, but in a way that does not produce premature reassurance or the impression that the hazard has diminished when what has changed is the model rather than the volcano. Both communications need to happen without producing confusion about the current monitoring situation or the current alert level, and without creating the impression that the agency's previous hazard assessment was simply wrong in ways that should reduce confidence in the current one. The revision is an improvement in the scientific basis of the assessment, not a correction of a previous error, in the sense of having used incorrect data or flawed methodology. The previous model used the best available data and methods at the time it was developed. The revised model uses better data and more advanced methods. That distinction matters for maintaining public trust in the hazard assessment process, but requires communication that most members of the public, who experience the change as a boundary revision rather than a methodological evolution, may not be equipped to make. The trust question runs beneath every aspect of the current situation, like groundwater beneath the volcanic edifice. Public trust in the monitoring agency, trust in the Civil Protection Authority, trust in the official communication, trust in the scientific process that produces the assessments being communicated. All of these are not fixed properties of the institutions involved. They are dynamic, built and eroded over time through the accumulated experience of people who have received official communications and compared them against subsequent events. At this volcano, the trust relationship between the monitoring agency and the surrounding communities has been built over decades of consistent engagement of community programs and liaison activities, and the cumulative experience of previous elevated activity periods that were managed without significant loss of life or major disruption. That accumulated trust is a real institutional asset. It is also not unconditional. It has been tested by previous events where the outcome differed from the forecast in ways that communities noticed and remembered. It will be tested by the current situation in ways whose character depends on how the situation evolves and how the agency's communication matches the reality that unfolds. If the current anomalous activity resolves without escalating to eruptive behaviour, the monitoring agency will face the challenge of communicating that resolution in a way that maintains the community's sense that the enhanced attention and preparedness actions were appropriate responses to genuine uncertainty, rather than an overreaction to signals that turned out to be benign. That communication is important for preserving the willingness of communities to respond to future elevated activity periods without the complacency that a string of false alarms can produce. If the activity escalates toward eruption, the agency will face the challenge of transitioning from the current cautious communication posture to the urgent, clear, actionable emergency communication that a genuine pre-eruptive crisis requires, without losing the trust of communities that may experience the transition as confirmation that previous communications were understating the risk. Neither of those communication challenges has a perfect solution. Both have solutions that are better than others, and those better solutions share the common feature of having been prepared in advance, of the agency having thought through the communication scenarios and developed the language and the protocols before the moment of pressure, rather than during it. The preparation of communication scenarios is part of the current enhanced operations at the monitoring agency. The public communication team has been developing draft communications for multiple outcome scenarios, including the scenario of activity resolving without escalation, the scenario of gradual escalation through the standard alert level sequence, and the scenario of rapid escalation requiring immediate high-level response actions. Those drafts are being reviewed by the Civil Protection Authority and by the regional officials whose public statements need to be coordinated with the agency's official communications. The review process is iterative and is not yet complete because the scenarios themselves are not fully defined, and the specific language appropriate for each scenario depends on details of the monitoring data and the hazard assessment that are still evolving. But the investment in advanced communication preparation is genuinely valuable because the quality of communication during an active crisis is consistently better when the basic frameworks have been developed before the crisis rather than improvised during it. The improvisation that happens during volcanic crises, when communication frameworks are not prepared in advance, is one of the consistent findings in post-event analyses of volcanic disaster communication failures. The Soufriere Hills eruption in Montserrat, which began in 1995 and continued for years, producing multiple episodes of escalating activity, evacuation, partial return, and re-escalation, is one of the most extensively studied cases of extended volcanic crisis communication management. The lessons from Montserrat about the difficulty of maintaining public trust through extended periods of uncertainty, about the psychological impacts of repeated evacuation and return cycles on a small island community, about the tension between scientific uncertainty and the public's need for clear guidance, have informed volcanic crisis communication practice globally. They are part of the professional background that the monitoring team and Civil Protection Authority at the current Volcano are drawing on as they navigate their own emerging situation. The Montserrat lessons do not provide a template that can be applied directly, because every volcanic crisis has specific features that distinguish it from every other, but they provide a framework of questions to ask and pitfalls to avoid that is more valuable than starting from first principles under operational pressure. The framework of questions includes ones that the current situation is actively confronting. How long can enhanced monitoring operations be sustained at the current tempo? The monitoring team is operating at a staffing level significantly above its normal baseline, with additional duty hours, additional analysis tasks, and additional coordination responsibilities, consuming the time and energy of personnel who are simultaneously trying to maintain the quality of their scientific work. That operational tempo is sustainable for weeks. It is not sustainable indefinitely. If the situation persists without resolution for months, the monitoring agency will face decisions about how to scale back the enhanced operations to a sustainable baseline while maintaining the sensitivity to escalating signals that the current situation warrants. Scaling back enhanced operations while maintaining sensitivity is an instrument design and protocol design problem as much as a staffing problem, and the monitoring team has begun thinking about what a sustainable, enhanced monitoring configuration would look like if the current uncertainty extends into the medium term. The medium term is a time horizon that volcanic crisis management situations regularly force monitoring agencies to plan for, even when the immediate focus is on the near term. Crises that resolve quickly are the exception rather than the rule. Most volcanic unrest episodes, including many that ultimately produce eruptions, evolve over months to years, with episodic intensifications and apparent remissions that test the patience and the planning horizons of the institutions managing them. The Campiflagre situation has been ongoing in its current accelerated phase for nearly 2 decades. The Long Valley caldera in California has been in various states of elevated alert for extended periods over the past 4 decades. Mauna Loa in Hawaii spent years in elevated seismic activity before its 2022 eruption, its first in nearly 4 decades. Each of those prolonged unrest episodes required the monitoring agencies involved to develop sustainable, long-term operational models for enhanced vigilance. Models that maintained the capability to detect and respond to rapid escalation, while not consuming the institutional resources required for that response in the course of simply maintaining enhanced operations over the long duration of the unrest. The 2022 eruption of Mauna Loa provides a useful recent comparison case that the monitoring team has been reviewing in the context of the current situation. Mauna Loa is a fundamentally different type of volcano from the current system, a massive shield volcano producing fluid basaltic lava flows rather than the explosive eruptions possible at a subduction zone system. But the seismic precursory sequence that preceded the 2022 eruption included a period of deep, low-frequency seismicity that preceded the shallow seismic swarm and ground deformation that are more classically associated with immediate pre-eruptive activity at Hawaiian volcanoes. The deep, low-frequency signals at Mauna Loa in the months before the eruption were recognised by the monitoring team at the Hawaiian Volcano Observatory as a potential indicator of deep system recharge, and they contributed to the elevated monitoring posture that the observatory maintained in the months before the eruption occurred. The eruption itself was preceded by a rapid and clearly detectable escalation in shallow seismicity and summit deformation that provided adequate warning for response. The deep signals were an early indicator. The shallow signals were the confirmation. The 2-stage sequence, deep anomaly followed eventually by shallow confirmation, is the pattern that the monitoring team at the current volcano is watching for, and the Mauna Loa case provides a recent example of that pattern playing out at a well-monitored system in a way that supported effective response. The differences between Mauna Loa and the current system are significant enough that the comparison cannot be taken too literally. Basaltic magma is more fluid and less gas-rich than the silicic to intermediate composition magmas that characterize subduction zone volcanoes. The eruption style, the hazard type, and the timescales of escalation are all different. The specific depths and spectral characteristics of the low-frequency tremors are different, but the conceptual pattern of deep signals preceding shallow confirmation is sufficiently general that it provides a useful framework for thinking about what the current monitoring data might be the beginning of, even if the specific details of the sequence are different at this subduction zone system than they were at Mauna Loa. The monitoring team has explicitly referenced the Mauna Loa sequence in its internal briefings as one of the historical analogues informing its current interpretive framework, while being careful to note the significant differences that limit the direct applicability of the analogy. Historical analogues in volcanology are both essential and dangerous. They are essential because the observational record of volcanic behaviour is limited enough that pattern recognition from historical cases provides a significant fraction of the basis for operational forecasting. Without reference to comparable cases from other volcanoes and other eruptions, the monitoring team would have very little basis for interpreting novel signals at a system that has not erupted in decades. But they are dangerous because every volcanic system is different in ways that matter because the historical analogues available are a highly unrepresentative sample of volcanic behaviour globally, biased toward the systems that have been most extensively monitored and most extensively studied, and because the human tendency to fit new observations to familiar patterns can lead to overconfidence in analogies that are superficially similar but mechanistically different. The monitoring team's explicit acknowledgement of both the value and the limitations of historical analogues in its internal discussions is a methodological sophistication that reflects the maturity of the scientific culture the team operates within, and it is the kind of intellectual discipline that the most consequential scientific judgments require. The most consequential scientific judgment still pending in the current situation is the one about whether the deep anomalous signals represent the early stages of a process that will eventually produce shallow confirmation signals and potentially eruptive activity, or whether they represent a transient perturbation of the deep system that will subside without engaging the shallow storage zone. That judgment cannot yet be made definitively. It will eventually be made by the geological process itself, which will either produce the shallow signals that confirm ascending magma, or will cease producing the deep signals as the perturbation dissipates. The monitoring team's job in the interim is to watch with the highest possible sensitivity and speed, so that when the geological process delivers its answer, the human response systems have the maximum possible time to act on it. The watching continues. The instruments record continuously. The data streams flow to the monitoring center. The analysis algorithms process each new data point and add it to the accumulating picture of what is happening 35 kilometers below the surface. The picture is incomplete. It is the best available picture. And in the gap between what the picture shows and what it does not yet show, 240,000 people are going about their lives, farming, working, raising children, watching the mountain that has always been there, trying to decide whether today is the day to take the emergency bag out of the closet and make sure it still has everything in it that it is supposed to have. The mountain gives no sign visible to the naked eye that anything has changed. The fumaroles steam as they always steam. The summit profile is unchanged. The birds that nest on the upper flanks are undisturbed. The farmers working the lower slopes notice nothing different in the ground beneath them. The difference is 35 kilometers below their feet, in a zone of rock that has never been seen by human eyes, and that reveals itself only through the faint, low-frequency trembling that the buried sensors are recording and transmitting, and that the monitoring team is reading with the focused attention of people who understand that the next entry in that record could be the one that changes everything. The next entry has not yet arrived. That is the honest state of the situation. Not resolved, not escalating. Suspended in the space between what the instruments can confirm and what the geology has not yet revealed. That suspension is not comfortable. It is not meant to be comfortable. It is the accurate description of where this volcano sits right now, and where the science of watching volcanoes sits more broadly, at the edge of what can be known. Pressing against that edge with better instruments every decade, still finding the edge. The 35 kilometers of rock between the surface and whatever is moving beneath it is not a large number in geological terms. The distance from New York to Philadelphia is larger. The depth of the deepest ocean trench is larger. In human terms, 35 kilometers of rock is an absolute barrier. No one will ever see what is happening down there. No drill reaches it, no camera documents it. The only window into that depth is the vibration it sends upward through the crust, and the scientists reading those vibrations are doing something that would have been impossible a generation ago, and that is still, by any honest measure, incomplete. What is known is this: the planet beneath populated land is not static. It moves on timescales that human civilization has not been present long enough to fully observe. The volcanoes that look permanent from the scale of a human lifetime are, from the scale of the geological record, intermittently catastrophic. The intervals between catastrophes are long enough that generations are born and die in the shadow of a mountain that has never done anything dangerous within living memory. The intervals are not infinite. The monitoring team will be at their stations tonight. The instruments will record. The data will accumulate. And somewhere in the next entry, or the one after it, or the one that arrives weeks from now, when the pattern has finally said something clear enough to act on definitively, the mountain will begin to answer the question that 10 days of anomalous tremors have been asking. The question is not whether this volcano will ever erupt again. The geological record answers that question. Every subduction zone volcano with a history like this one's erupts again. The question is always, only when? And right now, for the first time in a long time, when has stopped being a distant abstraction and started being something the people paid to watch this mountain are thinking about in a different way than they were thinking about it 2 weeks ago. The instruments are on. The scientists are watching. And the ground, for the moment, keeps its answer to itself.